Cool. And I think let's begin then, Nishant.
Yep.
Then I think, hey guys, I'm Rajiv, organizers for the Distributed Systems Meetup. So welcome to Distributed Systems Meetup. So today we have a talk by Abdul Karim on Hitchhiker Sky to Kubernetes networking. So we'll basically hand over to, before that, couple of announcements. So we kind of do this Distributed Systems Meetup every month. So if you are interested to speak in any of these meetups, you are more than welcome to basically send out a mail at dsconf. So we'll probably provide the email ID in the chats. And we also have a Telegram group where the discussions on anything distributed system happen every day. So if you are interested, please also join the Telegram group that is also shared in the group. Yeah, now handing it over to Abdul Karim for the talk. Abdul Karim, you can probably start with intro and then thank you.
Yeah. Hi, guys. First of all, I would like to thank Nishant and Rajiv, to organize this meetup and be available on a Saturday morning, and to all of you as well. Right? There could be 10 other places where you guys could have been. You could have just been in your bed. But yeah, thanks a lot for showing up. So let's start with today's talk. We'll be talking about some of the networking concept and how does Kubernetes networking work, right? Uh, so containers, basically in a distributed system like Kubernetes, they need to talk to each other, irrespective of the nodes they are running on, right? This talk will be an attempt to just demystify the underlying network magic by walking you through some key constructs like virtual Ethernet pairs, bridges, IP tables, etc. Right. Uh, so before we start, just a quick brush up on Kubernetes. I'll take a couple of minutes for the uninformed. Kubernetes it's an open source platform for managing containerized workloads and services. Right? It facilitates like declarative configuration and automation and stuff. It was open sourced by Google in 2014, and since then it has become a pretty large and it's a rapidly growing ecosystem with a lot of tool chain and utilities being built and maintained by communities. The major features that Kubernetes provides is service discovery, which means it allows you to expose your container or a set of containers using a DNS name or its IP address. It allows for automated deployments, which means you can declaratively describe the state of your deployed containers, and Kubernetes will ensure that it changes the actual state to the desired state at a controlled rate, right? Reliably. It also does bin packing for your services, right? So what bin packing basically means is you provide your container, or you tell Kubernetes what amount of CPU or memory or resources that your container would need, and Kubernetes will make sure or ensure that it will place your container on a worker node, right? So Kubernetes is a cluster of workers, so it will place your container on a worker node such that you make best use of your resources, right? So you don't have any unused or unwanted underutilized machines, right? So it bin packs your containers. And another feature, the last feature, is self-healing, right? So Kubernetes can take care of restarting your containers if they crash, right? It can replace your containers with new ones. Let's say if you're deploying something, it can even watch for containers if they become unresponsive, right? So you can define health checks for your services, and if they are unresponsive or if they don't respond, it will make sure that it replaces those particular pods, right? So yeah, these are the main features that Kubernetes provides. This is a very high level diagram of Kubernetes. On the left, the master node. This is also known as the control plane of Kubernetes. And on the right, you have the worker node, right, which is sometimes referred to as data plane, right? So all your workers, all your applications, all your pods, services, they are going to run in the worker node. right? You don't usually run any application level services in the master node. The key components of master node are the API server, mm, the controller manager, and HCD. HCD where all the metadata is stored, right? And on the worker side, you have kubelet and kube proxy, which kind of run the show. In this example, we see Docker as a runtime, but Kubernetes does support multiple container runtime, so this could change, right? Now, quickly, just walk through what are these components and what the roles are, right? So, what is an API server? An API server is a component that of Kubernetes that exposes the Kubernetes API to the world, right? It is a front end of the Kubernetes control plane, right? It is designed to scale horizontally, and you can just scale it up by adding more instances. You can run multiple instances of Kube API server and balance traffic between those, right? Next is kubelet. Kubelet runs in the data plane. So it is an agent which is running on your worker node. It makes sure that the containers are running in a pod, right? It will talk to the API server. It will get the list of pod specs or a specification, and it will ensure that it applies that specification onto that particular worker node. It also ensures that all the pods are running and they are healthy. Next is kube proxy. Kube proxy is slightly a misnomer. In the early days, it used to be a proxy which all the traffic passed through, but it no longer does that. It What it does is it primarily maintains the network rules on the nodes, on your worker nodes. So these network rules allow network communication to your pod from the network sessions inside and outside of your cluster, right? And how it does is it does it this by using the operating system uh, packet filtering layer, right? So, for example, it would use IP tables. Okay, so kube proxy is the guy who's going to deal with the IP tables. Then pods. Pods are like the smallest unit of computing that you have or that you can create and manage in Kubernetes. So in traditional Docker world, you have containers, but in Kubernetes, you have a meta concept called pods, which is slightly a level on top of just bare containers. So pod is a group of one or more containers which will share the network and storage namespaces or resources, right? A pod also has a specification of how to run the containers, right? So in a pod, usually you would have details like which image to pull, what tag to deploy, what environment variables to add, what is the health check or readiness check of that particular container running inside the pod. Okay, and finally, services. So services are an abstract way to expose an application running on a set of pods, right? So let's say you want to run WordPress. You have 3 WordPress pods. The way you would access it is you would create a service object which has these 3 pods as the backend, and uh, with every service you get a DNS name, right, which is resolvable within the cluster, and a VIP which exists for the lifetime of the service, right? So the pod IPs can change, the service IP will remain static. Cool. Moving on, let's consider a scenario. Let's consider a network 10.0.0.0/16, right? So this is a network that we have, a network CIDR, and there are 2 nodes running on this network. So if you are familiar with AWS, the network here we're talking about is a VPC, and the nodes that you see are your EC2 instances. Okay, both these machines are running Linux operating system, and this is important because the concepts that we'll be talking about, I mean, they may not apply as is on other OSs. So in reality, there would be much more smaller subnets or partitions of this network, and nodes would be placed accordingly. But in our case, it's just one big subnet, which means that both these nodes are part of the same subnet. And the cloud provider here is responsible of providing the network to us, right? So let's say if we think of AWS, so AWS in a way would be responsible for communication between these 2 nodes, which means if a packet is going to leave node 1, how do I check the pointer? Yeah, if the packet is going to leave node 1 and is targeted for node 2, we can assume that it will find its way to node 2, right? What happens between here, I mean, we are not worried a lot about it. So these two nodes are also part of a Kubernetes cluster, right? These are the worker nodes of our Kubernetes cluster, and each node is running multiple pods. So let's consider two such pods, pod A and pod B. So what we want to understand here is that if pod A wants to talk to pod B, which is running on a different node, uh, how would all this happen, right? So pod A can communicate directly with pod B using its IP address, right? That is the easiest thing to do. But that's not how it would happen in the real world. In the real world, and especially in a distributed system, using IP addresses directly, I mean, is not a very reliable means of communication, because IP addresses of pods, especially pods, I mean, they are ephemeral and they can change without giving any notice to the requester. So let's say if pod B here crashes, uh, the new pod that comes up in its place may or may not have the same IP. And I mean, there are very high chances that a new pod that get pod B is replaced with will have a separate IP, will not have the same IP. So what do we do? Uh, we bring in a service, right? A Kubernetes service. So as discussed earlier, a Kubernetes service is an abstraction or an alias for a group of pods or containers of the same kind, right? You can have multiple pods that are running behind service B, right? And these would be, let's say, application B. So you can have 10 different pods, and this service will, in a way, route traffic between all these pods. So services don't actually play any active role in routing the traffic. The Kubernetes service object, they just ensure that a DNS record is created, right, for service discovery purpose, and an endpoint is created. So here the endpoint is a Kubernetes endpoint, which holds the updated list of IPs for the pods belonging to a service. We will look at an example of a service and an endpoint later in the session, right? I'll show you some YAMLs and of a running service. So moving on, uh, the way pod A will communicate with pod B in real world is uh, it will resolve the DNS for service B, like step one. Uh, it will then get this IP address, which is a virtual IP address, which remains constant, right? The pods might come and go behind this, but this IP address is going to remain constant. And then what will happen is the IP tables would come into picture and eventually update the packet, right? Do a natting and replace this target with one of the backend pods. Okay. So to repeat, the packet starts here. The destination is service B, this VIP, and this VIP, this service knows, right, using the DNS and the endpoints, Kubernetes endpoints, that there are multiple pod Bs, instances of pod Bs running, right, and it would choose one of the IPs of these backend pods. So how does this all happen? Okay, these are so before we actually get into how this works, let's brush up some what do you say, basic concepts, networking concepts. We'll start with network models. Uh, we've all seen the OSI model, right? The Open Systems Interconnection model, right? Uh, it provides for a standard using which different computer systems, can talk to each other. It is like a language that networks speak, right? And it is based on the concept of splitting up a communication system into different abstract layers, right? And theoretically, there are 7 different abstract layers, right? When an application sends any information or data to another device over the network, it starts from the application layer and works its way down to the physical layer. And when a device receives data from another machine over the network, it starts from the physical layer and works its way up to the application layer. Okay. Uh, Next, we'll see about the TCP IP model, right, which is a slightly modified and a, I would say, minified version of the OSI model, right? So here the top three layers and the bottom two layers are clubbed together. Okay, so it has four layers: application, which is combined of app, presentation, and session layer, and you have the data layer, which is data link and physical layer. So the responsibilities of each layer more or less remain the same as the OSI model. We'll try to understand this using an example. Okay, so let's say there is a client application running on node 1, and there is a server application running on node 2, right? And client wants to send some data to the server. So how would this happen? So at every stage in this process, every layer will add some piece of information to the data, and this process is known as encapsulation. Okay, so we start at the application layer. This is the raw data that we need to send over to the server. So at the application layer, we have the raw data. This is passed down to the transport layer, where the TCP headers get added here. This is also known as the L4. This is also known as L4 in common networking technology terminologies, right? And the information it has mostly around the source and destination ports, right? So this would be the source port and this would be the destination port. Okay. Uh, at this stage, our data is known as a segment, right? A segment is then passed on to the IP layer or the network layer, where it gets the IP header attached. So at this layer, the packet gets to know where it is destined to, or which node it is supposed to go to. Okay. So this is just an example here. Let's say our source IP was 240.10 and our destination is 240.20. So the packet now knows where it is supposed to go, right? This is L3. And here at this stage, we call this data as a packet. And finally, at the data layer, the Ethernet frames are appended, so which contain information about the source and destination MAC address, right? So at L2 level, you deal with MAC addresses, right? You don't deal with IP addresses. So this is the last stage in the stack, and finally, after this frame is attached, the packet leaves the client node and it reaches the server node. Okay, on the server node, the opposite happens. The opposite of encapsulation happens, right? So and there are L2 level protocols like ARP, which are used by the network to guide the packet to the correct host. So once it leaves client one, how does it reach server two? I mean, we'll not get into the details of that, right? So once the packet has reached the server, the target host, where our server application is running, the reverse encapsulation process will start. So the host will first check the MAC address, right, and verify if it was destined for that particular server, right? If it matches, then these Ethernet headers are stripped off, and the packet is passed on to the network layer. Then it would match whether it's destined for for the host, right? If it does, then it's again passed on to the transport layer, and finally at the transport layer, the data finally reaches the application layer, right? So we started from data at the client and we get the data at the server. The actual encapsulated information is much more complex than what we have seen in this example, right? The headers are slightly more complicated and scary, but this just gives you an idea about how TCP IP model is used in networking. And to give a pretty non-technical analogy in short, this is similar to how postal service works, right? So if you want to send a postcard to your friend, you take a postcard, you start writing the name of your friend, followed by the street address, followed by locality, followed by the city, and then country, right? So here, you are the client, the postcard is the data, and the your friend is the server, right? So you are sending the postcard to your server, just like the client was sending data to the server. Okay. Uh, and when the post office or the postman tries to deliver the packet, the postcard, it works in the opposite route. So it will first look at the country, then look at the city, then the locality, and then the street address, and finally the name of your friend, right? So this is the encapsulation decapsulation analogy. Next we look at the IP tables. uh, uh, Most of us know of IP tables as just a firewall firewalling application which just allows or rejects traffic, right? It is just a firewall for us. But IP tables is capable of much more than that. And Kubernetes, or rather the container ecosystem, heavily utilizes IP tables for its networking functionality. Okay, so the man page definition of IP tables says that it is an administration tool for packet administration, for packet filtering and NAT. Okay, so IP tables is an administration tool for packet filtering and NAT. NAT is basically network address translation, which means that you modify either the source or destination address IP port of a packet. Okay, IP tables is made up of three basic structures: tables, chains, and targets. So the way IP tables operate is they compare the network traffic against a set of rules, and the rules define the characteristic that a packet must have to match the rule, right? And it also defines the action that should be taken for the matching packets, right? So there are many ways where you can, many options to establish which packet matches a specific rule. You can match the packet protocol type, right? You can match, let's say, if the incoming packet is TCP or UDP, you can match it based on the source or destination address, right? You can say if it's coming from, let's say, 192.168 or 10.0.0.20, whatever. And you can also use the interface that it is being used to. If you have more than one interfaces attached to your system, you can match the packet based on the interface and deal with the packets accordingly. The So the IP tables firewall uses tables to organize its rules. Okay, the most commonly used tables are NAT and filter. I mean, there are others, but you would rarely hear about them. So these tables classify rules according to the type of decisions they are used to make. Okay, for instance, if you have a rule which deals with network address translation, it would be put in the NAT table. Obviously, it's called the NAT table. And if the rule is used to decide whether to allow the packet to continue to its destination or drop it or reject it, it would be added to the filter table. I mean, that's simple. Next is chains. Uh, I mean, the tables, like we discussed, they are used to hold the rules, but the chains basically determine when the rules will be applied, right? I mean, a packet, when it enters a machine, an operating system, I mean, it has different life cycles, right? And based on which part of the life cycle it is, the appropriate chain is picked up. So, for example, these are the default chains available in IP tables: the pre-routing, input, forward, post routing, and output, right? You can also build your own custom chains, which Kubernetes does, and we'll see an example of that. Okay. Uh, let's look at this diagram to understand the previous example. So, firstly, if you have an incoming packet which is destined for the local system, so the packet would start its journey from here. It enters the network, the host. It goes to the pre-routing chain, right, followed by the input chain. And let's say if you have any filter here which says that drop the packet from this particular host, it would be dropped here itself. If it's not blocked, and if it's allowed, it passes on to the local process, right? And this process could be, let's say, your Nginx, right? And the packet could be your HTTP request. Second, incoming packets which are not destined for the current host, right, which are destined for the other host. A common example of this would be your Wi-Fi router, right? All the devices connected to your Wi-Fi router, they send traffic to the router, but I mean 99.9% of the times, or maybe even more, the packet is not destined for the router itself. It's destined for the internet. So the route that is taken in that case, the path it follows is it enters the host here, it goes to the pre-routing chain, followed by the forwarding chain, then the post routing chain, and it exits, right? It does not hit any local processes. And the third example here would be if your local process itself generates a packet, right? If your process itself wants to talk to the outside world. So what happens there is the packet first goes to the output chain. It looks for any filters in the table or any NAT rules that are to be applied. It goes to the post routing chain and then leaves onto the network. Okay. So the blue ones here are chains and the red ones are tables, right? This is an overview of how IP tables work. So let's look at a few examples. How would you configure IP tables? Consider that you want to allow SSH traffic from your office IP address, to the production machine or your jump machine. Okay, so this is basically how you would set an IP tables rule, right? -A means append. What you're doing here is you're appending the input chain, right? So we see here that any incoming request destined for the host is going to pass through the input chain, right? So you append the input chain, you see whether the protocol for that particular request is TCP. You look at the source IP address and verify if it's from your office, right? You look at the destination port. 22 is the default SSH port. I mean, if you're running on custom ports, you can change this. -T is for table. So you add a rule in the filter table, and the target finally is accept, right? So to repeat, you append the input chain, you add a rule in the filter table, and the target for that rule is accept, right? So this target can be accept, it can be reject, it can be drop, or it can even be another chain, right? So let me just repeat, the target here can be accept, reject, drop, or it can be another chain, right, in the IP tables itself. So let's see how does this look after it is applied. Okay, so once that is applied, you just do a list, right? You list the rules in the input chain of the filter table, and you see that your rule here is applied, that any traffic from the source with TCP protocol and destination port 22 should be allowed, should be accepted. Okay. Similarly, this is how you would drop everything from this particular host, right? You append the input chain, you add a rule in the filter table, and the target would be dropped. So anything and everything coming from this particular endpoint would be dropped at the input chain. Okay. It will still hit the pre-routing chain. You can do some manipulation there, but we are dropping it at the input chain. Okay, so now this is the fun part. This is where the meat of the today's talk lies, I would say. So how you can do much more than just accepting or rejecting a packet using IP tables, as discussed. So what we are doing here, what we're doing here is we are appending. So there's a chain called kube services. Okay, by the way, which is created by Kubernetes, and this IP here is the service IP, right? So we have a service with this IP, and we have 3 pods, right, running behind the service. So what we do is we first create a rule wherein we append kube services chain, and we say that any traffic that is destined for this particular IP, right, any TCP traffic with port 80 is destined for this particular IP. The target I want to apply is kube SVC 1, right? I mean, I could have said accept, reject, or whatever, but here I don't want to just simply accept or reject it. I want to do load balancing here, right? So any traffic that is destined for the service IP, the service VIP, it should jump to kube SVC A. Now let's see what kube SVC A is, right? So since there are 3 pods, you will have 3 rules for kube SVC A, right? So the first rule here does a probabilistic routing with a probability of 33%, right? So let's try to understand this. When a packet comes for this particular endpoint, it jumps to kube SVC A, and the first rule here is a probabilistic, what do you say, a random probability of 33% of applying this rule. And what happens if this rule is applied? It will jump to the service endpoint of pod A01, right? This means the traffic will be sent to pod A01, the first instance. If this fails to apply, there is in the next hop there is a 50% chance that this rule will be applied, and if this rule is applied, the traffic will be sent to the second pod of service A. And if this also fails, the third rule says that just send everything to service endpoint of pod A03, right? So what is this chain service endpoint pod A01, 02, 03, right? So here is an example. Whenever this this rule, this chain is applied, it will do a DNAT, right? It will do a destination NAT, which means the packet started with destination 100.64.171.186, right? But once we apply this rule, the destination will be changed to 100.96.2.10, right? And the port would become 8080 instead of 80. Don't worry if you don't understand this at this point. We will look at the same slide at the end of the session, once we have seen the walkthroughs of different scenarios, right? So this is how, in short, IP tables would you can do load balancing using IP tables. Okay. Uh, next, Okay. So when we talk about pod, I mean, we have covered the basic concepts of networking required to understand basic Kubernetes networking. We've talked about the TCP/IP stack, and we have talked about IP tables. So let's talk about a simple scenario. So consider a node with two pods running on them, right? So there's a node, there is pod A, and there is pod B. The node also has a network interface, ETH0. So now pod A here wants to talk to pod B, right? In the same node. How does that happen? So before we talk about that, whenever we talk about a pod, it's a slightly different concept than a regular container, right? A pod is a collection of one or more containers, right, sharing the same network namespace, right? Now, what is a network namespace? A namespace is a feature of Linux kernel which allows for isolation of resources, right? Which in layman's term would mean that a process that is running, or a container that is running inside this pod, I mean, is for all practical purposes unaware of what is running here, right? I mean, this pod is external to this particular pod, right? If there are two containers running within the same pod, in pod A, if you have two containers, I mean, they can talk to each other via localhost, right? Because they share the same network namespace. But Kubernetes will ensure that every pod will have a separate namespace of its own, right? And since we are on Linux operating system, the OS itself will ensure that there is a root namespace which is created on every node, right? So every interface has a root namespace, and all traffic that goes in or out, I mean, the root namespace is aware of it, right? It is a base of the networking layer of the operating system. Okay, so uh, yeah, so we've seen that pod A and pod B have different network namespaces, which means they are isolated from each other. So how do they talk to each other? Let's say pod A wants to communicate with pod B, and there is no direct channel, and there is going to be no direct channel. So the way they talk to each other is using VETH pairs, right? Virtual Ethernet pairs. How these are created, I mean, we will not look focus into that, but what they do is they basically create a pipe between network the network namespace of a pod, right, and the root namespace, right? So you send in data from one end, and it appears at the other end, like magically. And if you send in data from here, it will appear inside the pod magically. Okay, so with the network namespaces and the with pairs, the plumbing is done, and now the channel is available for communication between the host and the pods. So we'll see how can pod A send data to pod B, right? So the packet starts here. It gets laid onto ETH0 of pod A. The source IP is 1.10 and destination is 2.10. Okay. Over the VETH pair, it gets transferred and reaches the root namespace. At the root namespace, the bridge here, since all VETH pairs or all what do you say, Ethernet devices would be plugged into the bridge that you have here, right, on your host. It is aware of where to route this traffic, right? It acts as an L2 level device, and it knows which interface to forward the traffic to based on the destination IP, right? So in this case, it knows that for 10.0.2.10, it has to send traffic to v YY, right? So looks at the destination packet and knows that there is a routable interface available on the same node. So it sends the packet over to the v pair. Fine. So that's how the packet would reach your pod B, right? It starts from pod A, goes to the root namespace. The bridge will route it to this v pair, and the packet reaches pod B, right? And finally, it's in the correct network namespace, and it has reached a pod that can handle the traffic. So far, so good. We know how packets would move across in a single node, right? But since we are talking about Kubernetes, we are talking about multiple nodes, right? We are talking about a cluster. A single node is not going to cut it for us. And since we are dealing with multiple nodes, there are some requirements laid down by Kubernetes that the underlying network must adhere to. Uh, so whenever, so what are these requirements, right? So the primary requirement that we have is every pod must have an IP address, right? So every pod running inside the Kubernetes cluster must have an IP address, and these pod IPs must be routable, right? They must be reachable across the nodes, right? This is a requirement. Now, how does this IP address allocation work? I mean, this is basically taken care of by the IP address management module of the container networking interface that you're using, right? Some of the example CNIs are Calico or Flannel, right, which are free and open source. And there are also proprietary CNIs like Juniper, I mean, which help you manage the networking of your Kubernetes cluster. So every pod must have an IP address, and every IP must be globally routable within the cluster, right? The way this usually happens is whenever a new node is attached to the cluster, a new worker node, it gets assigned a CIDR, right? It gets assigned a special CIDR, and whenever a pod is created on that node, the node will use an IP address from within that CIDR, right, to assign the IP address. And Kubernetes really doesn't care about how you do it. There are multiple ways to implement it, right? But it just expects that all IPs are globally routable within the cluster. So let's look at an example of a multi-node setup, right? So we saw how pod A will talk to pod B within the same node. Now we see that we have two nodes here running in the same network, and they have multiple pods running. What we intend to do here is pod A should be able to talk to pod C, right? So a packet starts from pod A and it is supposed to reach pod C. Just like the previous example, the pod A will place the traffic on ETH0, which is a vETH pair. The packet gets transferred to the root namespace instantly, right? From there, the bridge does not know where the pod C IP is, right? Because clearly, since all interfaces are attached to the bridge, it has a map of what all routable interfaces it has. So it does not have any routable interface for pod C. So it places it on ETH0 on the interface, which eventually would place the packet on the network, right? So here is when the packet will leave our host, right? The packet is out of the host and on the network, right? It gets routed to node 2, and it is the responsibility of the network, right? So whatever happens here, and there could be multiple different things that happen here, we are not really concerned about it, right? So the packet has reached node 2. The ETH0 of node 2 knows that it needs to send the packet to the bridge, right? Because it has a mapping, and the packet hits the bridge on node 2. Now the behavior is same as the previous example where we had just one node, right? So the bridge will see that the destination address is pod C, and there is a routable interface with XX, right? Which it can use. It sends the data to the vETH pair, and the vETH pair will pump the packet into pod C namespace, right? And this is how the pod will reach our pod C from pod A in a multi-node setup. So Kubernetes networking, like we have discussed, demands that every pod will have an IP address which is globally routable within the cluster. But in the early days, the default container runtimes did not provide a mechanism to allocate unique IPs across a cluster. I mean, there were IP address collisions, and multiple pods running on different nodes, got assigned the same IP, and things were not compatible with how Kubernetes wanted them to be. So this problem was solved by overlay networks like Flannel or WeaveNet, right? Flannel, I guess, was the first one to come up with a solution for this. Uh, Although there are robust networking solutions which are operating, directly on L3 like Calico, which are now available, but overlay networks are still pretty popular, right? Uh, Also, introduction of an overlay network was pretty easy, as they would integrate well with the Kubernetes installation process itself, right? Overlay networks also provide some management features like setting up network policies and static IP allocation, subnetting, etc., which makes the life of an application developer much easier. So let's look at a multi-node scenario with an overlay network in picture. Okay, so in the previous example, just like the previous example, we have a multi-node setup where pod A wants to talk to pod C, but here we see that we have an extra Flannel 0 device attached in the root namespace of the node. Okay, so there is a Flannel device which is created in the root namespace of every node. So the packet starts from pod A and it wants to talk to pod C. It passes through the with pair, it jumps into the root namespace. But something interesting happens here, right? The bridge in this case is not aware of the pod IP for pod C, right? Because Flannel is taking care of that, right? When it hits the bridge, it wants to talk to pod C, but the ETH0 and the network in between, they have no idea about the pod IP addresses because they have been assigned in a different way in the overlay networks. So the packet gets routed to Flannel 0 device, right? And here the magic happens, right? This is the packet that started from our pod A and was intended to go to pod C. It had a payload, right? It moves on to the Flannel 0 device where it has a mapping of which pod is running on which node. Okay, so it looks at this packet. It sees that okay, the destination is pod C, and it knows that the pod C is running on node 2. So it will basically encapsulate the entire packet and add its own headers on top of it, right? So now in the new packet, the destination is node 2 and the source becomes node 1, right? So Flannel can take an IP and say the node IP, the Flannel can take a pod IP and say which node IP it belongs to, right? And Kubernetes can set this up by magic because Flannel is pretty well integrated in Kubernetes, right? It encapsulates the packet, puts a header on top of the packet with node 2 and the destination as node 1. Okay. So at the Flannel device, this is what happens here. Flannel has encapsulated, and now the new source and destination are node 1 and node 2. And Flannel would then place it on ETH0, which will in turn pass it on to the network, right? So the network knows that the destination node 2 is here, and we have the packet reaches on the ETH0 device of node 2. Again, since we are using Flannel, ETH0 here knows that this particular packet, right, node 2 is destined for our Flannel device. So it will pass it on to the Flannel device where the decapsulation happens of the package, right? Uh, yeah, so it passes on to the Flannel 0 device on node 2 where the decapsulation happens. Now the header that we had added, source and destination, are removed, and the packet comes back to its original form, right? Because this is how the packet looked initially. The source was pod A and destination was pod C. From here onwards, things again are similar to the previous example. The packet goes to the bridge. The bridge has a routable interface for pod CIP, which is with XX, and the packet reaches our pod C, right? The appropriate namespace. And this is how you would communicate using IP addresses in Kubernetes using an overlay network. But all these examples are using an IP address for communication, and we've already discussed that IP addresses are not durable, right? A real world cluster keeps on changing. I mean, nodes come and go. I mean, there are outages, there are scheduled downtimes, there are deployments, there are rollbacks that keep on happening in a cluster, right? Pods can crash, they can become unresponsive. I mean, Kubernetes can clean them up and bring up new pods in their place. So in all this, the idea is that the pods inside your cluster are ephemeral resources, and the IP addresses for the pods can change without any warning, right? So you need something that is more reliable than an IP address. We'll come back to the Kubernetes services example, and we'll see what exactly a service is. So a service, as discussed, gives you a virtual IP address, right, which is a long-lived static IP address which does not change irrespective of the life cycle of the backend pods it is serving traffic to. So for example, this pod A02, I mean, this may crash, this may die, or the node on which this pod is running may die. What Kubernetes will ensure that a new node comes up in its place and this pod is again scheduled, right? And this pod will be scheduled with a new IP address, but the service IP is not going to change. Okay. Uh, what a service also does is it creates a DNS name for this service, which resolves to the VIP, right? So your services basically talk to, so let's say pod A will talk to pod B using the DNS name of the service, right? So this is a more reliable means of communication as compared to directly using the IP address. Uh, yeah, so the client basically just needs a VIP, which it is going to get by resolving the DNS name of this service. This is an example service object which is already running on a cluster. Okay, so let's say we have a service, hello Kubernetes, which is running on a Kubernetes cluster. So if you query this object to the API server, it will return with a lot of data, but what we're concerned about is the cluster IP and the selector. Okay, so whenever you create a service, what you get is a cluster IP by default. This is generated by Kubernetes. This is assigned by Kubernetes, right? And you have a selector for a service, right? So what the selector bit here means is if you have 10 different containers in your Kubernetes cluster which have this particular label, right, which has this particular tag, app colon hello Kubernetes, and this service, this particular virtual IP is going to send traffic to all those 10 pods, right? So this is how the matching happens. And this is an example endpoint for this hello Kubernetes. Uh, this is the object for the endpoint object for hello Kubernetes. Okay, so like I've seen here, a service basically is a combination of an endpoint and a DNS entry, right? And endpoints are all the IP addresses of the running pods for that particular service. So we see there are 3 different pods running on 3 different nodes, right? And these are ephemeral. I mean, if node 2 goes down, there will be a new node which comes up in its place, and this IP is going to change, right? But the service IP that we have is going to stay the same. So let's look at the example where a pod communicates with other pod using a service endpoint, right? So the pod sends the packet, which moves out of the V pair and hits the bridge. This time the destination is not a pod IP, okay? It's a service, right? So it moves out of the V pair, it hits the bridge, and now something different happens here, right? So in this example, we'll see that since the destination is service IP, the virtual IP, right, for the service, IP tables is going to come into picture, and it is going to do the firstly it is going to do a DNAT, a destination NAT, right? Because we have defined a rule that whenever there is a packet which is destined for this particular service IP, right, do a DNAT, right? Assign one of the 3 pod IPs, right? So the IP tables is configured by Kubernetes to capture the traffic for the service IP. It also has a record of all the pod IPs that are running application C, right? It picks one of them at random and modifies the destination address of the packet. That is, it does a DNAT, a destination NAT. There is also contract. I mean, we'll not get into details of it, but contract is basically used to remember the source of the packet, right? When it comes back, right? The OS keeps a track of whatever changes were done to the packet. So once the denatting is done, the packet moves out of ETH0. Okay. It goes to the node to reaches the pod, whatever, and comes back pretty soon, right? Because services are running okay there. And when it comes back, you see here that the source and destination are flipped. So when it was leaving, our source was pod A, and destination was one of the pod C, right? Pod C001. And when it comes back, the source become pod C001 and the destination becomes pod A, right? But we cannot directly pass it on to pod A because the original packet did not look like this, right? There was denatting that happened. So again, using contracts here, the IP tables would do a source NAT in this case, right? Because it knows that it had sent a packet uh, which started from pod A and was destined for service C, and now it has received the packet back, and it is going to rewrite the source from pod C001 to service C, right? So things are transparent for pod A in this context, right? So pod A doesn't know what happened in between, neither does pod C, right? So IP tables in a way takes care of all of that. So you do a DNAT, there is a contract. When the packet comes back, there is a SNAT that happens. Okay, and the packet finally returns back to pod A. Okay, so there is often a confusion about how does IP tables work here? What does it do? Who sets the rules for IP tables? What are the rules for IP tables? So this is the simple algorithm that Kubernetes follows. Okay, so if the destination IP matches a service IP, a service VIP, right? What the IP tables will do is it will pick one of the pods for the service that is defined here and rewrite the packet. So if we look at the example, we had a packet which started here, right? We had pod A, and the destination was service C. So we have a service C which is running in Kubernetes, right? So the condition matches here. If the destination IP matches a service IP, it will pick one of the pods for service A and rewrite the packet, do the DNAT, right? And this is the sample rule. So this is our service IP, 171.186. It matches this destination IP, and what it does is it passes it on to the kube SVC A chain, right? So, okay. I'm not sure why this. Fine. Ignore that. There's some bug here. I don't know. So we were looking at the rule of IP tables, which does the routing part, picking up a pod and rewrite the packet. This is the same slide that we saw in the beginning of the talk, right? So a packet comes in with the destination 171.186, right? It jumps to the kube SVC A chain. Kube SVC A chain has 3 different rules, right? And probabilistically, it will route, or you can say randomly, it will route traffic to one of these nodes, right? Typically, it should be a 33% chance that pod A 01 will get the packet, or pod A02 will get the traffic, or pod A03 will get the traffic, right? And finally, this is the DNAT rule which gets applied. So yeah, mm, that was about IP tables. And in the beginning, we had briefly discussed that kube proxy is a component that runs on the worker nodes of your cluster. I mean, it is a service which is present on every node, and it is responsible for updating the IP tables as per the service definition. So who updates the IP tables rules? Kube proxy updates the IP tables rules. And there is also a DNS component. So when we say that every service will have a DNS which resolves to its VIP, there's a kube DNS component which runs as a pod. And when you create a service, Kubernetes will ensure that there's a DNS entry created in that particular DNS service, and that is resolvable from all the pods within the cluster. Okay. So yeah, I guess that's it. That's it for the talk. I'm open for questions. If you guys have any.
Thanks, Abdul, for the talk. Folks, if you have any questions, you can unmute yourself and ask Abdul, or else I can take questions from the chat too.
Hmm, how do I see the chat? Okay, here. Chat.
Okay, I think let's take few questions from the chat then.
Mm-hmm.
So I think Raghav Garg asked, so do the Kubernetes service use some load balancing algorithm for routing the traffic between all the pods?
Yeah, so by default, the example that we've seen here is what will be used. How do I close this Q&A wala thing? Whatever it is. How do I go back to the slides? Hey Rajiv.
Yeah, can you?
Yeah, how do I go back to the slides? I mean, I've clicked on something and I'm here.
Not sure. Like, can you stop? Is there a stop button anywhere? Or you can probably close this and reopen if that helps.
Okay, let's do that. Just give me a minute. I'll restart this presentation. Yeah. So this is the default load balancing algorithm that uh, Kubernetes will use for a service, which is a random probabilistic distribution, and it will distribute equal traffic across all the pods, right? So if you have 5 pods, all the pods will get 20% of the traffic, right? If you have 3 pods, like each pod will get 33% of the traffic. But it is probabilistic, right? It's not a round robin by default. You can configure it to do so, but by default, this is how it behaves.
And this probabilistic chain rules are getting updated every time my pod changes through Q proxy.
Yeah, so every time, so let's say one of your pods goes down, okay,
Okay.
the endpoint object will be updated, okay. Uh, we saw here that a service. So a service basically creates a DNS entry and an endpoint, right? And a Kubernetes endpoint is a collection of running pods IP addresses. So the life cycle of the pod will ensure that whenever it is created or destroyed, an IP gets added or removed from the endpoint object, right? And that endpoint object is used to ensure that the entries here are updated frequently.
So since this is a probabilistic model, you said, and every rule has to be changed whenever I have a new pod.
Not every rule would, yeah, every rule would have to be changed if you increase or decrease the number of pods, right?
Yeah, let's say I am seeing some scale in my application
Mm-hmm.
because of some campaign that I'm running.
Right.
So every pod that comes up will actually go back and change every rule.
If you scale up your pods, probably yes, but you don't have to do it manually, right? It is managed for you. I mean, this is something which is transparent to the user.
Okay, understood. Understood.
Yeah.
Thanks. Thanks.
Yeah.
Yeah, I think people should be able to mute themselves and ask questions. Yeah.
Yeah, I have a basic question. So, usually it's an IP which uniquely identifies your location. So, what does the MAC represent? Doesn't the IP uniquely identify you in the network?
Mm, yeah, I mean at the layer 4 it is IP address, but at Ethernet level, at level 2 it is the MAC address, right? So it's a mix of both. You need a pair of IP address and a MAC address, right, to be able to reach to your target.
Can I ask a question?
Yeah, sure.
Yeah, hi. I want to know what is the specific advantage of overlay networks, because I couldn't figure out based on the headers that were added by Flannel and then it was again removed at the other end. What specific benefits does Flannel offer, or any kind of overlay component that you introduced?
Mm, I mean, so let's say you want some. Let's go back to the slide there. Talking about. Right. So let's say you have a network, right, and you have a CIDR that is assigned to the network. You might want to scale your services. You might want to add more nodes, but you might hit a restriction where your IPs are limited, right? So in that case, what you would want is to set up an abstract layer of network on top of the existing layer. That is one of the use cases. One problem that we discussed during the talk was that when Docker or any container, runtime creates pods or containers, right, on the host. What they did was they in a way started with a standard 172 whatever domain, and if you had two different nodes running containers on Docker, there was a high chance that both of them would get the same IP address. And Kubernetes requires, it demands that every pod should have a unique IP address which is routable, right? So if there's a IP collision, things are not going to work well. So overlay networks kind of came in and solved that problem. But like I said, there are new technologies which kind of help you to not use overlay networks at all. So I think Calico is the most popular one. So it works it works using the BGP, border gateway protocol, and is much faster than overlay networks as well, right? So overlay networks were something that were used to solve a problem, which is now solved using the basic OS level construct.
So overlay networks in this case, like Flannel, was well integrated in Kubernetes. So that integration allows it to see through all the nodes and what pod has what IP, and it can bridge that gap quickly. Is that what the benefit is?
Right, that is one of the benefits. Yes.
I see. Understand. Thanks. That was a wonderful session. So thanks for answer and the overall session. Thank you.
Okay. Thank you.
Can I just add one small thing to this earlier question?
Sure. Sure.
So I think basically the idea of any network overlay, any external network like Falco and Calico, Fannel and Calico, is basically to ensure like the cluster itself is networked, because each of the platform itself needs a basic network routing for the individual containers, correct? So by default, if you don't, let's say you don't put any network, you add on network onto it. So how does the networking happen between the pods at all, right? Because each of them are isolated units, correct?
Mm-hmm.
So I think that is where the CNI comes in and says that you
Right.
need to have any one of the networks like Flannel or Calico. You just cannot leave it like a unique system alone, standalone.
Right. Right. So Kubernetes has left that responsibility on the CNI, right? It no longer cares about how do you do that. It only cares about every pod should have a unique IP, and every IP should be routable within the cluster.
Correct. So because until now we are dealing with only one machine, like a Linux box or a Windows system. So that system had an IP, and we didn't have to worry about how the traffic was, because that was handled by the cloud backend, the DNS and everything. But now we are creating a mini kind of a distributed system within the same box. So then the concept of having our own network comes into picture.
Yes.
What is the CIDR? What does it represent?
A CIDR is basically a representation of a group of IPs, right? So it basically defines a range of IPs that are available in that particular network. So for example, if I have one single node and the IP address of that node is 10 dot 10 dot 10 dot 10, for example. So 10 dot 10 dot 10 dot 10 slash 32 would mean that you just have one single IP address, and the slash 32 here is basically the bit. I mean, right? So there are 32 bits in an IP address. So 10 dot 10 dot 0 dot 0 dot 16 slash 16 would mean that you have the entire range starting from 10 dot 10 dot 0 dot 1 to 10 dot 10 dot 255 dot 255, right? You have all those 16 bits. So you just define, so it's just a shorthand of giving a range of IP addresses, a CIDR.
It's something like a subnet mask.
Yeah, I mean, yeah, you define subnet mask with a CIDR, but you have a CIDR for that.
Okay.
Mhm.
Hey, I have one question regarding Flannel again. Yeah.
Mhm.
So, yeah, so what I understand is like input to Flannel will be all the nodes that you have in your Kubernetes cluster, right?
Okay. What do you mean by
No,
input
no.
to Flannel?
So it's kind of like so Flannel will be running as a separate process of its own, right?
Mm-hmm. Mm-hmm.
So basically the thing is like when you are building a Kubernetes network, you will tell Flannel, okay, these are the machines I have in the basically these are the IP addresses of the nodes I have
Mm-hmm.
in my cluster, and
Mm-hmm.
then it's your responsibility to give me kind of like a unique IP address for each and every pod or service I create. Is it like
Mm-hmm.
that? Is it like that, Flannel?
Yeah, I mean it runs as a separate process.
Okay.
It does keep a map of the pod IPs and
Mm.
which node that pod IP was allocated to, and it stores this
Okay.
information in HCD, right? So every Flannel
Yeah. Okay.
device, every node will have a process which is talking to HCD, and it has an up-to-date information of which pod IP is allocated on which node,
Okay.
right?
Okay, so it uses HCD to make sure, okay, an IP address that, so Planel is kind of like it will assign IP address, or it's kind of it will just make sure no two pods have same IP address. Does it does the job of assigning the IP address too?
I mean, yeah, it should do that. I've not specifically read on that part, but
Okay.
it in a way helps in the routing of the packet primarily, right? So
Okay.
when an interface receives a packet with a destination that it does not know about, it can look up to Flannel and say, okay, fine, do you know anything about this, right? And if it is a valid pod IP address, Flannel will have the information and it will encapsulate the packet with the target node IP.
Okay, so the other question is basically you use UDP in Flannel. So let's say my pod is sending a TCP packet.
Mm-hmm.
Okay. And then what I saw is like Flannel encapsulated on a UDP. So,
Mm-hmm.
so what about that?
I mean, yeah, that's just an implementation detail, right?
Okay.
Probably, again, the user need not worry about that. It is just about how the packet is going to reach the target node.
Okay. Okay. Yeah. Thanks. So one question, like I think someone else also asked here, which is basically about service meshes.
Mm-hmm.
So I think, can you like, yeah, service meshes. So if when we are done with other questions, can you just talk about like what are your views on service meshes?
Okay, sure.
Yeah. Yeah. Anyway, other guys can ask their questions after that. Like if time permits, we can actually just have a small.
Sure.
Okay.
I think the concept of using UDP is, correct me if I'm wrong, is basically to ensure that it is guaranteed instead of a TCP connection.
TCP is guaranteed, right? UDP is fire and forget.
TCP is guaranteed with you get
Yeah, yeah, you get acts and stuff.
yeah, you get ACK and NAC
Yeah,
and
yeah.
all of that.
UDP says okay, you send it. If I get, yeah, that there's a joke, right? No one gets the UDP joke. Yeah, that's why.
I had a question regarding like when you're using Flannel, is it still necessary that all pods have a unique IP, or it's okay if that is not compliant to?
Yeah, all pods must have a unique IP. That's always there.
Then I didn't get like why would you use Flannel to create another overlay network? In the sense like then Ktos itself would be able to route and do the stuff right with services or whatever.
So KTS itself does not do it, right? It has left it onto the CNI, the container network interface, And Flannel is just one of the example CNIs which uses overlay networks, right? If you don't want to get into the overlay network mesh, I mean, you can use something like Calico, right? Which has an option of using overlay networks, but you can just use it as is, right? But Kubernetes itself does not do any networking magic there. It's a separation of concern.
So one of the services way that you showed, is that a mechanism where the packet is transferred from one pod to another pod without any CNI, or even in that case there is a CNI somewhere in between?
Which one?
You showed I think two mechanisms of transferring traffic, right? One was with Flannel overlay and one was with just services definition.
Services here.
Yes.
Yeah.
So here, is there Flannel or some CNI playing some role, or there is?
I mean, there cannot be. There can be or there cannot be. It depends.
So so if you don't have any CNI or any such thing that takes care of.
There will be a CNI always. I mean, there can be an overlay network or not, but CNI will always be there, right? With any Kubernetes installation.
Okay. So in this case, is it like say Kubernetes has some default CNI that does this here?
Yeah. So the default these days is Calico.
Okay.
Yeah. That's what you'll get if you create a new fresh cluster using Kops, for example. Right? Kops is a CLI utility to create clusters. So if you're creating a new cluster, you'll get a Calico network CLI.
Okay. Thanks.
Cool. And I think if we don't have any more questions, then we can wind up this meetup. Thanks, Abdul, for your talk. I have also shared the Telegram link for the distributed systems Telegram group. So you can join that group and you can have the discussions post meetup. Thank you, Abdul. Thank you
Yeah.
all.
Thanks, Rajiv. Thanks, guys. Thanks a lot, and have a good weekend. Bye.
You too. Thank you.
Yeah, thanks for
Thank
the
you.
talk.